Okay, I think we're ready to get on to differentiability now. Now, don't fret too much. This will be much quicker than before. Okay, you remember there were 3 parts to the continuity definition, right? There are also 3 parts for differentiability, but it's f-x for each one. Just have a look at your definition and the 3 parts for continuity, and it's saying f of x is this and f of c is that, and the limit of f going this way and f going that way is the same. So for something to be differentiable, it's all of that, but for the derivative instead of the graph instead. Okay? So, what would it mean? What does that mean? Well, usually, we'll think about it this way. I'll give you 2 examples. If something is not continuous, okay, then it certainly cannot be differentiable. Okay? Because there's breaks in the function itself, so that means there must be breaks in the derivative too. Okay? But there are functions that are continuous, and they may or may not be differentiable. Okay? Is differentiable, is not differentiable. Okay? So, most of the ones that you've been dealing with so far come under this heading. Okay? The function's continuous. It's, like y equals x squared minus 5x plus 6. Something simple like that. Okay? That's continuous. There are no holes in it. You differentiate it, and you get this, which also has no holes in it, so everything's happy. Okay? But there are some important examples you need to get where it starts off nice, but then when you differentiate, you get problems. Okay? So let's start with one you're really familiar with. The absolute value of x. Absolute value of x. Okay. Now I'll admit, this is a bit sneaky, because really it's not one function, but 2. Okay? But let's think about what's happening here. I'm not going to answer the question of differentiating it yet. I just want to look at it. Okay? So this is what the graph looks like. Okay? Now, it's a continuous function, because number 1, there are no breaks. Number 2, I can draw the whole thing. In fact, I did draw the whole thing without lifting my pen. Okay? And you can think about the limit as x approaches 0 from this side, and as it approaches this side, everything's fine. Okay? But then when you think about the gradient, something's wrong. Okay? So for instance, as I approach the origin, okay, what's the gradient doing on this side? What is the gradient of any point on this branch? It's 1, right? Gradient 1, 1, 1, 1, 1. So, if I took the limit as x approaches 0 from the positive side, okay, the derivative, the gradient, f dash, would be 1. Because look at it, it's like 1, 1, 1, 1, it's approaching 1, okay? But when you take the limit from the other side, okay, you can clearly see the different kind of behavior. It's a decreasing function over here. It's minus 1, minus 1, minus 1, minus 1, all the way up to, I'm not including the origin. Okay? So seeing as the derivative, therefore, can't be defined at the origin. So we say y equals the absolute value of x is not differentiable at this particular point that we're interested in. Okay, and that's a really important idea to get across. Okay, it's continuous there, but it's not differentiable there. All right. Now, let me give you question.
What is y equals root x squared?
Root of x squared. Yeah. Okay. You can plot points. It's not as bad as say x squared on x, which has a discontinuity in it.
No, but root x squared, right? Isn't that the same as
Yes.
Yeah.
Yes. Okay. Now, I just want to give you one more counterexample. Again, a continuous function that isn't differentiable at a particular point. Okay. That is, and I want you to have a go at graphing it first before I show it to you. Maybe you're familiar with this shape. I'd like you to graph this. What does this guy look like? Cube root of x. That's x to the power of the third. You could plot points. That would not be that bad an approach. Or you could think of it in terms of, you know, when we've been thinking about functions and relations, that kind of thing. I can redefine this as, I can cube both sides. Cubing both sides is not as bad as squaring both sides because these two are equivalent. I haven't gotten rid of negative solutions by cubing both sides. Okay. Now, what would this look like? Well, you guys know what y equals x cubed looks like, so what would happen if you swapped? It would just go sideways, right? So one side looks like this. It's sort of like it's sort of like the square root of x, but it goes shallower faster. Just like x cubed goes steeper faster, right? It's an inverse function. What does the other side look like? It's an odd function, right? It has odd symmetry. Okay. So there's the cube root of x. Now you can see, this ticks all the boxes for continuity, does it not? It's defined at all points, and it's if you take the limit at any two places, if you go from both sides, you'll get the same value. Everything's fine. Right? But then you differentiate. So, dy on dx. Now I rewrote this in index form, because it's a little easier to deal with, because this is just power rule, right? So, what do I get when I differentiate?
1/x minus 1/x to the minus.
Bring the power at the front, and then you reduce the power by 1, which gives you a third minus 1, which is minus 2 over 3. Okay, now let's just rearrange this a little bit. That's a negative power, right? So it's 1 over 3x to the power of 2/3. Okay, so now can you see why there are problems creeping in? Okay, because this derivative doesn't exist at a particular point, namely x equals 0. Okay, now why is that? So if I were to draw a tangent there, right? Well, actually, I already had drawn the tangent because the tangent at the origin is the y-axis, right? And of course, a vertical line doesn't have a gradient because gradient needs run. It needs horizontal movement, horizontal change, and a vertical line doesn't have any horizontal change. It's just there on a single point. So therefore, we say, just like with the absolute value of x, it's continuous but not differentiable at x equals 0. Okay, and this particular example, cube root x, will come up again later when we look at graphing. It's this weird graph that's always got problems with it. Okay, so we'll come back to it again.